Imagine a world just beyond our grasp that once echoed with life. A world bathed in sunlight, teeming with water, perhaps even breathing an atmosphere not so different from our own. Now picture that world stripped bare, its oceans evaporated, its atmosphere vanished, leaving behind a cold, red desert hauntingly silent. This isn't science fiction. This is Mars, our nearest planetary neighbor, a celestial canvas on which an epic story of planetary evolution, loss, and the enduring possibility of life has been painted. For decades, humanity has gazed upon this rusty orb, first through telescopes, then through the eyes of robotic explorers, each mission peeling back layers of dust and time. And with every new discovery, every rock analyzed, every ancient riverbed mapped, a profound question resurfaces. What did NASA know about this planet's vibrant past, its potential for life, its lingering secrets, even before they could fully piece the puzzle together? What were the whispers in the data, the tantalizing hints that pointed to something far more extraordinary than we were initially told? The truth, as it turns out, is a story of cautious science, revolutionary data, and a growing understanding that Mars holds far more secrets than we ever dared to imagine. For centuries, Mars was a canvas for our hopes and fears, a distant mirror reflecting our own terrestrial existence. Early telescopic observations, often distorted by atmospheric conditions, and the limits of technology fueled wild speculation about canals built by intelligent civilizations. Percival Lowell's detailed maps, published in the late 19th and early 20th centuries, captivated the public imagination, depicting a dying world where a desperate race engineered waterways to survive. While these visions were ultimately debunked, they etched into our collective consciousness the idea of Mars as a place capable of hosting life, perhaps even advanced civilizations. Then came the dawn of the space age. The first flybys and orbiters of the 1960s and early 70s, like Mariner 4, 6, and 7, delivered stunning, often stark, images of a heavily cratered, seemingly lifeless world. The dreams of canals and bustling Martian cities evaporated, replaced by the grim reality of a cold, arid desert. It was a sobering blow, yet it only intensified the scientific imperative. Was Mars truly dead? Or was there still a chance, perhaps for microbial life, clinging to existence in some hidden niche? This question culminated in NASA's ambitious Viking program of the mid-1970s. Twin landers, Viking 1 and 2, touched down on the Martian surface with one primary directive: to search for signs of life. Equipped with sophisticated miniature laboratories, they scooped up Martian soil and subjected it to a battery of experiments. One of these, the labeled release, LR experiment, yielded truly startling results. It involved mixing a nutrient solution with Martian soil. If microorganisms were present, they would metabolize the nutrients and release radioactive gas, which the detector would register. And it did. The LR experiment returned positive results, strong, consistent signals that seemed to scream, life. The excitement within the scientific community was palpable, yet quickly tempered. Other experiments on Viking, particularly the gas chromatograph mass spectrometer, GCMS, designed to detect organic molecules, found none. Organic molecules are the building blocks of life, and their absence was a significant red flag. How could there be life without its fundamental components? The prevailing scientific consensus, after much debate, was that the LR experiment's positive results were a false positive, likely due to peculiar, non-biological chemical reactions involving highly reactive Martian peroxides. NASA, always cautious in its public statements, concluded that Viking had found no definitive evidence of life. But here's where the "what NASA knew" theme truly begins to resonate. What if those initial LR results were more significant than officially acknowledged? What if the absence of organic molecules detected by the GCMS was simply because the landing sites, chosen for safety, might have been too sterile, or the GCMS was simply not sensitive enough to detect trace amounts, or even that the procedure heated samples to too high a temperature, destroying any organics? For some scientists, the ambiguity was a profound one. They had a tantalizing positive result, countered by an inexplicable negative. The official narrative shifted to one of no life found, but the internal scientific discussions, the lingering doubts, the what if, certainly persisted within the agency. They knew they had a mystery on their hands, and the definitive answer remained elusive. The decades that followed Viking saw a paradigm shift in our understanding of Mars, driven by a new generation of NASA missions. The Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, and the rover's Spirit, Opportunity, Curiosity, and Perseverance began painting a picture radically different from the barren world of early Mariner images. They revealed undeniable evidence of a watery past, a Mars that once flowed with rivers, collected in vast lakes, and perhaps even harbored a northern ocean. Orbiters provided stunning images of ancient river valleys, delta formations, and features strikingly similar to shorelines. Spectrometers detected minerals like hematite, jarosite, and various clays, which on Earth form only in the presence of water. The rovers drilled into rocks, finding direct evidence of hydration, carbonate deposits, and evaporite minerals. This wasn't just fleeting moisture. This was a Mars that was warm and wet for potentially hundreds of millions of years, an immense period during which life could have not only emerged, but flourished. The what NASA knew slowly transformed into what NASA was definitively proving. Each new mission built upon the last, chipping away at the old, dead planet narrative. We learned about massive subsurface ice deposits, even at middle latitudes. We detected seasonal dark streaks on crater slopes, called recurring slope lineae (RSLs), initially interpreted as flowing briny water, though later research suggests they might be granular flows triggered by surface hydration. Even if not actively flowing water, the initial hypothesis shows how desperately scientists were looking for present-day liquid water. Then came the tantalizing radar evidence from the Mars Express orbiter, a European mission, but heavily scrutinized by NASA scientists, hinting at stable liquid water, possibly brine, beneath the southern polar ice cap. Beyond water, NASA's missions began unraveling the mystery of Mars's lost atmosphere. Data from the MAVEN, Mars Atmosphere and Volatile Evolution Orbiter unequivocally showed that Mars lost most of its early, thick atmosphere to solar wind stripping, a process that continues today. This confirmed that Mars once had a much denser atmosphere, capable of sustaining liquid water on its surface and providing a protective shield, just like early Earth. The timeline suggested that this thicker atmosphere coincided with the period when liquid water was abundant, a crucial factor for the emergence of life. NASA didn't just know Mars had water. They began to understand why it lost it, and what that implied about its early habitability. Perhaps one of the most intriguing and persistent mysteries to emerge from NASA's ongoing exploration is the detection of methane in the Martian atmosphere. On Earth, methane is largely a byproduct of biological activity, think cows, microbes, rotting vegetation. But it can also be produced by geological processes, such as serpentinization, where water reacts with certain minerals. The European Space Agency's Mars Express first detected methane in 2004, and NASA's Curiosity rover later confirmed its presence, detecting significant, localized spikes in methane levels within Gale Crater. These spikes were baffling. They appeared and disappeared rapidly, suggesting a currently active source. This is a profound, what NASA knew moment. They knew methane was there, and they knew it was highly variable. But the source remains elusive. Is it biological, hinting at active, subsurface microbial life? Or is it purely geological, suggesting ongoing geothermal activity? The implications of either answer are immense. If biological, Mars might not just have harbored ancient life, but could still be a living planet. If geological, it suggests an active interior, possibly with hydrothermal vents that could also support life. NASA scientists have meticulously tracked these methane variations, attempting to pinpoint their origin, but the answer remains locked within the red planet's crust. It's a compelling signal, one that demands further investigation, fueling missions like the ExoMars Trace Gas Orbiter, ESA, with NASA instrument contributions specifically designed to study these atmospheric mysteries. And then there are the organic molecules. The absence of these building blocks of life in Viking's GCMS data was a major reason for the initial no-life conclusion. But curiosity, with its more advanced SAM sample analysis at Mars Instrument, changed that. In 2018, NASA announced that Curiosity had detected a diverse array of organic molecules, including thiophenes, benzene, toluene, and small carbon chains, preserved within ancient sedimentary rocks in Gale Crater. These weren't necessarily signs of life itself, but they were the crucial ingredients, the very molecules that form the foundation of all known life. This discovery was monumental. It confirmed that the necessary precursors for life were present on Mars billions of years ago, coinciding with the period when liquid water was abundant. It directly contradicted the initial Viking interpretation and showed that organic molecules can survive the harsh Martian environment, at least when protected inside rocks. This profoundly altered the what NASA knew about Mars's chemical environment, shifting it from a chemically inert place to one rich in the potential for life. So, where does this leave us? The journey from Percival Lowell's canals to Viking's ambiguous signals, to the overwhelming evidence of a warm, wet past, methane spikes, and organic molecules, is a testament to scientific perseverance. NASA, through its decades of tireless exploration, has methodically peeled back the layers of Martian history, revealing a planet far more dynamic and potentially life-friendly than anyone once imagined. The what NASA knew isn't a secret conspiracy. It's the evolving, incremental understanding gleaned from rigorous scientific inquiry. It's the initial, tantalizing positive from Viking's LR experiment that couldn't be definitively explained, planting a seed of doubt and possibility. It's the slow, painstaking accumulation of data from subsequent missions that consistently pointed towards a past that could easily have fostered life. It's the current, frustratingly ambiguous methane signals, pushing the boundaries of what we consider possible for present-day Mars. The story of Mars is far from over. Missions like the Perseverance rover are actively collecting samples that will one day be returned to Earth for analysis, a monumental endeavor that could provide definitive answers to the presence of ancient Martian life. The Europa Clipper mission is heading to Jupiter's icy moon, a prime candidate for current extraterrestrial life. Each new mission, each new dataset, brings us closer to understanding our place in the cosmos and whether we are truly alone. What enduring secrets does Mars still hold, waiting for humanity to uncover, forever reshaping what NASA and all of us truly know?